I think chemistry, first and foremost, is about atoms, how the atoms are linked into molecules. And I think the majority of chemistry, when you think about it, has been, at least in the 20th century, has been concerned with molecules, with discrete entities, clusters, molecules, discrete entities. So chemists know how to do that very well. What I want to tell you about today is how we've taken chemistry from discrete molecules into the extended structure regime. And why do you want to do that? Is that when you think about the most useful materials that make up our world, synthetic materials, they're really extended structures. You're not going to build bridges out of proteins and molecules. You're not going to build the next fast airplanes out of molecules and DNA. You're going to build them out of extended, robust structures. And so the question is, I think, how do we combine robustness with molecular precision? Molecules are wonderful because we can precisely design them, put functionalities wherever we want. We can also characterize them with great definitiveness because of X-ray diffraction and other techniques. So I'm going to rank on this slide materials in terms of their robustness and in terms of the ability to design them and control them on the molecular level with precision. Okay? So extended inorganic structures like metal oxides, traditional solid-state materials, they're very robust but not highly designable. Okay? And forgive me if this is not as accurate as it should be or as rigorous, but in general, it's really true. Nanoparticles and polymers, they're highly designable or not so robust, and actually not, I should say, not so designable. We can't control their chemistry, not so well, especially structures of polymers. If you change the side chain of a polymer, you change the structure, and sometimes in an unpredictable way. Metal complexes, supramolecular structures, biological molecules, they are the epitome of precision in terms of their design, but they're not terribly robust. So the question is, can we combine this robustness with the molecular control and precision? Because if we can, not only would we have extended chemistry to extended structures, but also extended structures that can be designed, that can be functionalized, and that can be tailored for very specific function. And so there's a problem. If you want to take molecules to 2D and 3D, you have to link them together through robust bonds, through strong bonds. And the very first thing that I was taught as a student, you can't do that because you're going to make amorphous materials or ill-defined materials. And so you need to be able to make crystals. So you face immediately the crystallization problem. Anytime you try to link molecular building units through strong bonds, you will face the crystallization problem. So the crystallization problem is that if you're linking things through weak bonds, you're more likely to be able to crystallize them than if the bonds get stronger. Even hydrogen bonded things are much easier to crystallize. Coordination networks, because of these weak bonds, metal ion to Lewis base type nitrogen or lone pair linkers, such as these, are only around 60 to 90 kilojoules per mole, depending on which metal you're talking about. So they're weak bonds. But you can crystallize structures based on this kind of linkage. What happens when you go up here, or even here? Those are very strong bonds. Okay, that's what happened. We made metal organic frameworks from now metal ions that have Lewis base lone pair, but also a charge. That makes your bond a lot stronger. These bonds, these metal carboxylates bonds, are as strong as a carbon-carbon bond. Same thing here. I won't talk about these so much, but the ultimate is covalent organic frameworks, which is covalent bond. Now, when I was a student, you wouldn't have dreamed that these would ever be made. So that was the birth of what we call reticular chemistry, which is the control of the strong bond. This is supramolecular chemistry, the control of the weak bond. Reticular means net-like. Okay, it's used very frequently in physiology, but not in chemistry. So we introduced it into chemistry. It's net-like. It's the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. This definition has three things that are very important. One, you're linking molecular building blocks because you want to do things in a rational way. You want to be able to design. Two, they have to be strong bonds so that you can make robust materials. And three, they have to be crystalline so that you know what you're working with and you can characterize them. And so in this way, we showed the feasibility of this approach back in '95. We examined their porosity in '98, and we showed the exceptional porosity in '99 for the metal organic frameworks. I'll talk more about this. The covalent organic frameworks, we made the 2D in 2005, and in 2007, the 3Ds. And then if I have time today, I want to share with you a new approach to reticular chemistry, which is molecular weaving. How do you make structures that are mechanically interwoven? Okay, so there's nothing new under the sun. Let's talk about porosity in metal organic compounds, in things that I would be talking about. The very first compound that showed porosity was made by Alfred Werner. And in fact, if you go to Switzerland, University of Zurich, in one of their labs there, you can find the original samples that were made by him and his students. And this is one of the compounds, and it traps a benzene unit in its crystal. Richard Barrer, who is one of the inventors of zeolites and is credited for the template effect in zeolites, studied its porosity and showed that you can actually remove the benzene and introduce gases in its place. But the problem was, okay, this is the nitrogen going in and then saturating the pores. The problem is that when you put the benzene back and you cycle, the structures collapse. Why? Because they're linked through weak bonds. Okay, so the material became non-porous. And then Stephen was talking about Prussian blue. Prussian blues are porous. They are probably the oldest porous materials known. And they're made from iron and cyanide. Okay, I don't consider these moths because the cyanide is not functionalizable. Okay, the essence of organic chemistry is that you can vary you can functionalize the units. And these are metal cyanides that are layered and they trap molecules between the layers. I think the very first example of metal organic porous structures or open structures was in 1959. And this you will find in Wells' textbook, Solid State Chemistry. And it's basically a copper 1 that is linked by adiponitrile. This is a copper +1, and then the nitrogen is the same nitrogen I'm talking about with the lone pair, the weak bond, but nevertheless it assembles to make an extended structure with open space, and in the open space you've got nitrate floating around to balance the charge. This some of you will recognize that it's based on the diamond network. A German group in 1986 showed that you can do the same by varying the guts of the linker. Okay, it's a little bit of a squiggly linker, diamino dinitrile, but you make the same kind of net, open net. In 1989, Robson showed that in fact you can take the tetracyanide or the tetranitrile and link it together with copper 1 using exactly the same kind of chemistry. So then I come along in '95 with hundreds of these being reported every year. This field was called crystal engineering. And we started making similar things, copper 1 with bipyridine and nitrate in the pore. And I would go to meetings, to Gordon conferences, give a talk, give a poster, and everybody would attack me for showing this and calling them porous. And they're right, because nobody has proved their porosity. Nobody really has proved that they can be open in the absence of guests. And so we started exchanging the nitrate with chloride to see whether the frameworks remain intact. And in fact, they were not very stable. They were not stable because they're made from weak bonds, and they were also made from intersections that had only one metal ion. Okay, so that's very, I call them unsteady, very wobbly. So these, what I call coordination networks, collapse upon removal of solvent. They're not designable, and they're not chemically stable. And if I continued in that area, I would not even get tenure. So I had to do something, and as an inorganic chemist, immediately I realized that instead of a single metal ion, go for a cluster to be at the intersection. The cluster can act as an anchor to the whole framework. And so I knew this cluster very well. This was very famous when I was a student. This is a di-zinc or di-copper acetate structure, and here are the 4 acetates. It's called paddle wheel, and then you have 2 water molecules that terminate as terminal ligands. Well, from my point of view, from reticular chemistry point of view, this unit can act as an intersection, and it can link along these 4 directions. And indeed, if we succeed in doing this, you've made a rigid building unit. It's directional, and it has one kind of geometry. Copper 1, the examples I showed you, they could be tetrahedral, could be trigonal. You couldn't guess what you're going to get. But here, you can always count on this unit to act as a 4-coordinated, and it has strong bonds, as strong as carbon-carbon bonds. So this was our SBU, not Stony Brook University, but secondary building unit. So the SBU approach, we used it to make this structure, which is we call Moth 2. You can see Moth 2 is made from those paddle wheels, but now with terephthalate. If you mix all this stuff together, you will not get a crystal. You will get amorphous stuff or poorly crystalline stuff. And the only way that this student was able to make crystals is that he dissolved these in DMF and then diffused from a toluene solution triethylamine, rather than just add the triethylamine directly. By diffusing it, by first diluting it and diffusing it slowly, he was able to control the deprotonation, because as soon as you deprotonate this, it binds to the zinc. Okay, so if you can control that deprotonation, you can control the crystallization. And that's how we made this structure. This structure is basically a square grid structure with the pores filled with DMF molecules. And the big question was, if I remove the DMF molecules, will the structure remain open or will it collapse? And so to do that, you have to do what is called gas adsorption isotherm. And the shape of the isotherm, here you see nitrogen going into the pore, and in the open circles coming out of the pores. So this is adsorption and desorption, and the same thing for CO2, adsorption and desorption. Well, the shape of this isotherm tells you that this material is permanently porous. Okay, and this is the golden standard, the gold standard for measuring porosity. The porosity was rather low, 275 meters square per gram. So it was kind of disappointing to us. So we published this paper, and I got 3 excellent reviews. I sometimes share them with when I'm giving a student talk. And since then, I haven't gotten 3 positive reviews on a paper. But now you have kind of a low surface area. You know, zeolites, people were reporting 500 meters square per gram for zeolites. I was happy. I was the only person happy about this development because it allowed us for the first time to say that these moths, a combination of organic and inorganic, two areas of chemistry taught separately, can be combined into one area. That's one. And two, we can compare them to the established materials like zeolites. So people didn't really pay attention to moths until we reported Moth 5. And with Moth 5, we found that in fact DMF and DEF, of course, when you heat them, they release small amounts of base, and that small amount deprotonates the acid, and that gives you, again, control of the kinetics of the reaction and control of the crystallinity, and that's why you can make crystals of this moth. This is Moth 5, and it's made from tetrazinc building units, SBUs, linked by terephthalate. The yellow ball is there to illustrate the space within which molecules can be incorporated. As soon as we reported this paper, there was an explosion of moths because the surface area of this compound was 2,900 meters squared per gram. 61% of the crystal is open space. Okay? Now we know how to activate Moth 5 so well that the surface area is actually 4,500 meters squared per gram if you evacuate the pores fully. And this is what the structure would look like. It's an extended three-dimensional structure. You can see the isotherm is what's called type 1 isotherm, indicating permanent porosity.
How do you define Langmuir surface area?
This is calculated based on the amount of nitrogen that is absorbed. Okay. So we now report both Langmuir and BET surface area to make sure that both numbers are known. So in the literature, in the original papers, we reported the Langmuir surface area, but then we started reporting both the Langmuir and the BET surface area. So this SBU approach turned out to be extremely powerful because if you know the conditions under which this SBU forms, you can add different organic linkers. And you can make them functionalized and incorporate them into the structure, or you can expand them to make larger pores. This was quite powerful. No one has managed to do anything like this in solid state compounds. And so we knew that we were onto something. Showed and went on to show that not only can you use paddle wheels in the tetrazinc, but also you can use many other building units, including rod-shaped SBUs, not just discrete SBUs, but also rods, metal oxide rods that can be linked by organics. And we and others have been exploiting almost the entire periodic metals in the periodic table with organic linkers, simple ones, and more elaborate ones, longer ones, elaborate ones, even ones that have metal binding units, they can be exposed into the pores and later metallated. So you can see as long as you have carboxylates, you can make a moth. Later, of course, we and others have shown that you can use almost any kind of anionic organic, not just carboxylates, but you can use imidazolates and others. And you can see even things that you would think cannot be linked into an extended structure. This is 11 phenylene units. You can make moths out of that. These are ditopic linkers. Even tritopic linkers, simple ones, more complicated ones, as you can see here, even linkers that are porous in themselves. Tetratopic ones that link along 4. All of these have been made into moths, porphyrins and expanded porphyrins as well. More tetratopic linkers, okay, even ones with polyethers, cyclic ethers, and boranes, even chiral linkers, tetratopic linkers, pentatopic linkers, hexatopic linkers of all kind, octatopic linkers. okay? And dodecatopic linkers. Okay, my message here is that if you can think it, you can make it. This is rare in chemistry. Okay, synthetic chemists know how powerful it is that now I can think up a structure I want to make, and I can find the building units from the vast inorganic and organic chemistry and make materials that later I'll show you can be functionalized and used. Well, we have then developed this periodic table of reticular chemistry. Basically, if you can define the shape of your building units, you can combine your building units and make these nets. Okay, so each one of these nets has been made as a moth, all right, from these combinations. And let me just say that if you just look at this box, that is vast chemistry in itself. Because think about the different triangles, different compositions, different sizes, and therefore different materials with different metrics. Think about all of that chemistry. That box alone will take a whole career to actually develop the chemistry of and understand the chemistry of. So all of these, and that's why this field is so large, because each structure offers different opportunities and potential for new chemistry. So not only those shapes, but also more complex shapes, and even more complex and furthermore complex. And you can see that there are still boxes for anybody who is interested in entering reticular chemistry to challenge themselves and make these still to be known frameworks. All right, so why we wanted to know, why are moths so highly porous? Why do they have this extraordinary porosity? We took a crystal of Moth 5 and put it in a capillary and reduced the temperature to 30 Kelvin. Usually, if you do that to single crystals, they will crack. They lose their monocrystallinity. But for this moth, it didn't crack. And we can actually take a single crystal structure of it. And you can see proof that the structure, this is 90% ellipsoid of the structure without anything in the pore. This is the ultimate proof of permanent porosity. I remember years ago, many years ago, when I showed the isotherms of moths and we did not have a crystal structure of the pores like this. Kim Dunbar was sitting in the front and she said, why can't you get a crystal structure of the framework? Well, that was an impossible experiment in those days, right? But we did, because these are amazing materials. This structure, if you look at it carefully, the reason it is so mechanically stable is that the carboxylates are 90 degrees to each other. This carboxylate is turned 90 degrees to this, and it's also 90 degrees to that. And that's the best way to build any kind of structure. Okay, if you look at a barn, how the barn is built, it's built on these opposing 90-degree constructions. So we introduce small amounts of gases to see where they sit. And so we find that argon sits on the metal oxide unit, and so does nitrogen. So this is a major adsorptive site. But what we also found that was very surprising is that the gases also sit on the faces of the six-membered rings and the edges. And the edges, these kinds of interactions were never observed in gas phase, in the old-fashioned gas phase chemistry. So that means that for me to make a very porous material, I have to expose as many edges as I can. And so Moth 5 was a very good example of that, but you can still do more. If you, instead of 1 phenylene unit, you could use 7 phenylene units, and now you have plenty of exposed faces and edges, including the exposed metal oxide units. And so you have a material here that, now I'm quoting the BET surface area, 6,400 meters square per gram. Langmuir surface area is 10,000 meters square per gram. Okay? And they're very open. So unlike any other porous material, the pores have no walls. So things can diffuse in and out without clogging the pores. And so this then the source of this extremely high surface area is that they are just scaffolding with exposed edges and faces and intersections. And that's, so everything you're looking at is an adsorptive site, and that's why they have extremely high surface area. So over the years, we and others have been, let's say, competing for high surface area. And here's Moth 5. In the original report, exceeded the traditional materials. The French came in, and they couldn't beat us. We reactivated Moth 5. And at the same year, we reported Moth 177 because now we knew the key to high surface area, so we went to 4 phenylene units. And then the French came back with vengeance and beat us. And then this is Zhou Zhao from Texas A&M, the French, us, and then us again, retaining by activating Moth 177 better, we can get a higher surface area. This is the optimal surface area of Moth 5. And then Michigan group, this is the French, the English, the Michigan group, us, Northwestern, us. Okay, then the Germans, the English, and then this is one of my former students in Pittsburgh, Nat Razi, the Germans, the Northwestern group, held the record for a while, but then to be beaten recently by the German group. Okay, so that is the most porous Moth you'll ever be able to make. Okay, unless you go to structures that are full of acetylenes. Okay, that's because acetylenes would assemble the largest number of gases around them, since the carbon is only 2 connected. So if you do that, if you have a structure full of acetylenes, you will be able to more than double this surface area. Okay, but it probably would be making an explosive. So the surface, so many times in chemistry, you have an objective and you never can get there because there are a lot of problems along the way. In Moth chemistry, determine your objective and you will get there. The chemistry works. So now, a student, we wanted to prove that not only can you have high surface area, but that the pore opening can be very large, so that not only can you incorporate gases, but also large molecules, maybe even biological molecules. And for that, you need to make Moths that have pore openings that are on the nanometer scale. And so this student started here. This is the parent structure. And I asked him to make, I didn't ask him to make this at the outset, because most students would run away if you tell them to make a Moth out of that linker, right? So I learned a lot on how to present a project to a student. And the more ambitious you are, the less likely it's going to get done. So don't tell them the ambitious stuff until they get their first success, okay? So you say, okay, make this. And so the student went away and made it. He made a larger porous. And then I said, well, why not make another phenylene unit? And then he said, okay, let's publish. I said, no. If you go to 4, if you go to 4, you will break the record in pore opening. It will be the largest pore opening of any porous crystal. And so, of course, and he knows implicitly that if he breaks the record, he gets a science paper or a Nature paper, right? So he did. But after this, he did all of this on his own, right? After this, he was so enthusiastic, couldn't sleep at night, that he said, well, I mean, if 1, 2, 3, 4 work, then 5 should work. And you can see here we put methyls to make it more soluble and therefore be able to control the crystallization better. But he went all the way to 11 phenylene units. Okay. When we sent this to, we actually first sent this to Nature. You can imagine that a lot of work went into this. Because not only does he have to make the material, he has to do their crystallography and everything. Porosity, everything. I mean, this material here is very porous. We measured the porosity of this material. And so we sent it into Nature, and we got 3 reviewers, 2 reviews. So two reviewers combined, they got together and they combined their review, which I think is unethical. But anyway, that's what we had. We had two reviews from three reviewers. And of course, the two that combined their effort, they combined their effort not to say how brilliant it was, but that they didn't believe in any of it, that all of this was just fictitious. I don't know who they are, but they know nothing about crystallography. So basically, nature gave me a major revision. And I just thought, how can I overcome two reviewers that, one, they don't know anything about crystallography, and two, they just want to reject the paper. So I withdrew the paper from Nature. I said that I'm afraid I'm not going to get fair reviewing with you. And then we sent it to Science. Before we sent it to Science, we did TEM on the Moths and showed beyond any doubt that in fact there are pores there. So these are the open pores, okay? Look at that. We can put hemoglobin in there. We can put GFP in there. This is not even the largest member, but nevertheless it fits a large biological molecule. So this will open a whole new area where you're now operating on very large molecules as guests. Okay, so what I want to do is I want to discuss two applications of Moths. And one of them is CO2. And CO2 is a problem. Just as chemists, just think about this equation. This is octane. Let's say that your fuel is made of octane, I assume for the sake of the simple calculation. And you combust in your car, 24 kilos. That's how much probably in an average sedan. You have emitted 81 kilogram by the time you burn that fuel tank. That's a lot of CO2 that's being emitted into the atmosphere. So that tells you the scale of the problem. And the technology that is out there that people are thinking about is a very old technology that was used to capture carbon dioxide from natural gas. When you're mining natural gas, there's around 10 to 20%, depending on where it's mined, of CO2. And the way you capture that CO2 is you pass it through an aqueous monoethanol amine solution. So aqueous solutions of this toxic, corrosive liquid. And then after you have captured the CO2 to make carbamates, you heat to 120 degrees to remove the carbon dioxide, compress, and store it under the ground. Okay, all of this is pretty ugly stuff. Like I said, the ethanol amine solution not only is toxic and corrosive, but it degrades. And because you're heating water solutions, the heat capacity of water is very high. And so you're using potentially 30 to 40% of the power output of a power plant just to capture the carbon dioxide. So immediately from our point of view, we were thinking, if you could capture carbon dioxide in a Moth is a solid, and Moth heat capacity is 1/10 the heat capacity of water. You should be able to do it with energy economy. So we used this zinc Moth 74. This Moth has a rod-based SBU. And here you're looking directly at the point of the rods linked by organic. Okay, how does this Moth do? This is, we made the magnesium. This is the data for the magnesium Moth 74. You see in a natural gas wave of 80% methane and CO2, you expose a powder of magnesium Moth 74 to this mixture of gases, and you see no CO2 coming out. It's captured in the pores and pure methane coming out. Okay, that's a beautiful separation. Okay, you have the solid, natural gas comes in, CO2 stays in the pore, methane comes out. Unbelievable. The problem is that when you're trying to separate carbon dioxide from combustion gas, you have water around. And when you have water, it competes for the adsorptive sites where CO2 sits and kicks the CO2 out. And so the material becomes very inefficient in the presence of water. So to address that, here's the CO2 in the pore. We know from crystallography that CO2 binds to the open metal site in this magnesium structure, and other CO2 molecules are very weakly interacting with that. But this is where chemistry comes in. You have a crystal of the Moth, and now you functionalize it with the same amine type of unit that they use in the liquid. Okay? And you make carbamate. So, and you can prove with carbon-13 NMR that in fact you are making the CO2-bound material. This is the experiment I just described. This is called a breakthrough test. You take the mixture of gases with CO2, and then you pass it through the Moth to purify those gases or to bind the CO2. So how does it do when you functionalize with the amine? This is the data. When you functionalize with the methyl without water, very nice separation, stays in the pore. When the pores are filled with CO2, it breaks. Now notice that with methyl functionalized, if I add water to the system, to the gas mixture, the efficiency of the material goes way down. Now, with the amines functionalized, dry or wet, your breakthrough time is exactly the same. So the separation is not affected by water. This is the very first time that anybody showed that, in fact, you can take a material like a Moth, functionalize it, and show beyond doubt that the water is not affecting the separation. In fact, water, we found later, helps in the binding of CO2 to these amines to make carbamate. So what this means that the scientific challenge of capturing carbon dioxide from power plants is solved. Okay? The rest is just engineering and economics and the will of society to capture the carbon dioxide. The next problem I want to discuss is the problem of water. Okay, the red-orange areas are in trouble. Basically, you have about 60 to 80% of the water reserves used up, and they're not getting replenished. So these are arid areas, either don't receive enough rain, or they are using much more than they can replenish. So 1/3 of the world population lives in these water-stressed regions, and another thing to know is 160 countries import their water. So it's also a national security problem for different countries. Luckily, there is plenty of water in the atmosphere. Okay, this is not Stephen's salary. This is okay. There is as much water in the atmosphere as we have in rivers and lakes, around about the same amount. So there's plenty of water, and so we need a way to capture it. Now, if you Google water harvesting, you'll get a lot of this stuff. These are just dehumidifiers that work in humidity over 60%. Okay? There is nothing out there that works at low humidity. Most of those red regions, the humidity levels are around 35, down all the way to 5. There's nothing that works under those conditions. So here's another map. Okay, those dehumidifiers I showed you will not work in any of these regions. So there's zero, the red regions, there is 0 months out of the year where you can directly cool the air to get the water out. Okay, so this from here to here, these regions, direct cooling like your dehumidifier does will not work in harvesting water. Okay, so that's the potential that we have. These regions here are ice. They're already, the water has frozen. That's why you can't use dehumidification. But it's these regions that we want to address. So why is it so difficult to trap water from low humidity atmosphere? Look at these psychrometric charts. basically you have temperature here increasing in this direction and humidity increasing in this direction. And at low humidity, to be able to get to the dew point, the point at which the air is concentrated with water that you basically condense water, you have to cool down to very low temperature. This is over here, could be 0 degrees Celsius, maybe even less than 0 degrees Celsius, to be able to concentrate enough water in the atmosphere to condense. And so our idea is that if you have a moth that traps water from the atmosphere, okay, you can increase the humidity within a container and therefore not have to cool down too much to be able to condense. And so our idea is to take dry air where the dew point is less than 0, okay, put a desiccant in, a Moth desiccant that traps water from this atmosphere, and now your dew point is 27 degrees Celsius, okay? And now you can condense the water. And so we discovered this while we were studying CO2 capture and separating CO2 from water and the function of water in the separation. We discovered this behavior in red. This is the uptake of water. Now this was amazing to me because it's binding water at levels of humidity around 20%. This is 20% relative humidity. And the next amazing thing was that you can remove it at 45 degrees Celsius. Okay, that's low temperature, which meant that if I have this material in the desert, I should be able to trap water during the night, and then during the day, it comes out, and if I have it in a container, I can condense it. Notice that the Moth works in and out, the water in and out, in and out. This is over 80 cycles. Notice that there is a drop after the first cycle. Those are seeds of water or ice granules that sit inside the Moth and attract the water. Okay, I'll show you in a second what I mean by that. This is the Moth, and these are, depending on the pressure of water or the amount of water going in the pore, you form tetrahedral water molecule clusters and you make cubes. These are the seeds. Remember, the Moth is inorganic, organic. The inorganic attracts the seed. The organic repels the water. But the water from the atmosphere is attaching itself to the seed regardless of the framework. The framework is just there to contain it. And that's why you see that drop. That drop, these seeds we do not harvest. We don't take out. Those stay in the material. So that works in the lab. It works beautifully. Does it work outside the lab? So being a synthetic organic chemist, I thought, well, maybe I need a mechanical engineer to help us build a device. So I went to MIT, to Evelyn Wang, with whom I was collaborating before, and we built a small device, just as small as your palm, and basically it's like a glass jar with a lid. On the inside of the lid you have the Moth, and at night it's exposed. During the day you close the lid or you close the jar and put it in the sunlight. The inside of the jar heats up. You can see here the inside of the device heats up, and as it heats up, the water comes out of the Moth into droplets, and you can see the droplets getting larger and larger as the temperature is, or as time and temperature increases. Okay, so we reported this in Science, and immediately after that there was publicity, and MIT went to Evelyn Wang and said, we give you tons of money, just don't work with Omar. This is all MIT's. And so they didn't know who they were messing with. My students will not allow it. And so we built our own device. We hired a mechanical engineering postdoc, and together with us, we designed this box within a box. Okay? The inside box has the Moth. It's exposed at night to desert air. During the day, you close the outside box, you put it in the sunlight, water comes out of the Moth, concentrates the atmosphere with water, condenses on the walls, and now you have puddles of water. Okay? So this is what it looks like. Just a plastic box within another plastic box. So these guys, these three, Farhad from Iran, Marcos from Germany, and Eugene from Ukraine, Russia. He's a Ukrainian Russian. Got together and rented an SUV, a black SUV, and drove from San Francisco to the desert in Arizona. And they had 1 kilogram of moth with them, a white powder. This is the zirconium moth that I just showed you. And of course, I sent with them a letter signed by me and the dean that says, this white powder is okay. And all the wires that you see for measuring humidity and the sensors for humidity and so on, this is just all has to do with an innocent chemistry experiment. And so I asked them to update me at every point in their experiment. And so after 2.5 days, they have not updated me. I don't know what's happening. I don't know whether they were taken away by the sheriff. I don't know whether they got into a fight. I have no idea. So I picked up the phone at 2 o'clock in the morning and I said, what is going on? And they were all awake. So I knew there was some problem. And they said, we see fog inside the box during the day, but no condensation. Okay, so the moth takes up the water, and during the day, it takes the water out, the water comes out, it's a fog, but it does not condense. It turns out in a desert, you have this box, and so the sun is everywhere. It's heating everything, okay? So I said, well, why don't you put the box under the ground, part of the box under the ground, and under the ground is around 2 degrees or so less, and you should be able to condense. And so they called within 1 hour and they said, oh, it works. They were in an Airbnb. I hope they did not dig up the ground too much. But that was a successful experiment, and they harvested, depending on the day and the weather, 0.2 to 0.3 liters of water per kilogram of moth. Okay? If I want 100 times that, I just use 100 kilos of moth, and they sit in a corner and they harvest the water. So we asked the Ukrainian Russian to drink the water. This is supposed to have, okay. Yes, okay. You heard him say nice, right? It's actually distilled water. It doesn't taste nice. But it's quite inspiring. This is ultra pure water. We tested it for metals, organics. There's nothing in there. The company that we started sent the water that they harvested using this moth to the FDA, and it passes with flying colors. So the moth itself is a filter. You're also taking gas to liquid. I mean, there's many different purification steps. The nice thing about chemistry that works all over the periodic table is that you can go from zirconium to aluminum. Zirconium is very expensive, $160 a kilo. Aluminum is very cheap. So you can make an aluminum moth that not just does as well as the other moth, but even better. This is Moth CO3. And for this one, we send the students to Mojave Desert, okay? And I don't know how they found this motel in the middle of nowhere. It's really a flea motel. And we designed a system of cartridges. So you have cartridges of moths. Air comes in one direction, and then you pull in the other direction. So while you're collecting water from the atmosphere, you're pulling water in the other direction. Now, this experiment, this is the harvested water. This is the humidity that measured in the desert during the experiment. Notice that the humidity goes very low, 7% relative humidity during the day. During the night, it varies, but it can be as high as 60 and as low as 35. But notice that at every point, we are collecting water. Okay? This water came from Berkeley. That's the first That's the water that was in the Moth when it was in Berkeley. This was the first measurement in the Mojave Desert. I told these students, don't come back without a video showing how you're collecting the water. And so this is the drops of water. There is a bug that shows up and moving around. I don't know if it should do that soon. There it is. No. Okay. So this is Nikita. He is a Kazakhstani, German, Russian. Okay. And this is a full-fledged local American. He's a professor, used to be my postdoc. We rented him from his professorship in South Alabama to help us with some of the energy calculations and things like that. And this is a French postdoc. And this is the Mojave Desert, the driest desert in North America. And they can harvest water from this device. We hooked up the device to a solar panel so that we can do more than one cycle a day. If you have power, you can always push air in, collect the water, and do this many times. So they harvested 1 liter of water per kilo of moth per day. Okay, that's pretty impressive. But we can do better because these are moths and they have very open structures. And so the kinetics is even faster than we can imagine. This is the kinetics in and out of a zeolite, or water coming out of a zeolite. This is coming out of CO3. And so if your kinetics is fast, you can have the pumping of air and collecting water to be also fast. So you can do many, many cycles during the day. And so this is now in our company, which we are commercializing, and we will soon unveil a system that is as large as your old-fashioned coffee maker, that will deliver 8 liters per day. And that's not from a kilogram of moth, but from less than 100 grams of moth. And that's because the kinetics is fast, so now every 3 minutes, you can do a cycle. You can pump air in and take the water out. Later, we will unveil a system that's as large as a small dormitory refrigerator that delivers 260 liters per day. And then engineers, by the way, are wonderful. As long as chemists are open-minded to work with engineers, great things will happen. Because without engineering, we could not have used less than 100 grams to deliver 8 liters per day. Okay? So, but they have a way, with our help, to expose every granule of moth to maximally be exposed to the air. And so we do have plans that within a year we will be able to get to over 20,000 liters per day. So what have we done? We've made water mobile, off-grid, personalized, and it's ultra pure. It's a dream come true for me personally because I was born in a desert region and I know how it is to live in non-watered areas of the world. But the nice thing about this is that it works at all humidity levels. Right? In fact, it works easier in areas where there is plenty of water, but it's not pure. Right? You can do that. Think about areas of the world where there's plenty of water, but it's not pure. You can harvest water even better so it works at all humidity levels, and you deliver ultra pure water that you use for drinking. Of course, you have to mineralize it like your city mineralizes your water for drinking, but also you can use it for agriculture, for any kind of application. Okay, my next story is not as long. It's a shorter story because I want to keep track of the time. And it deals with the work. I want to introduce it by introducing the work of Lewis. We all know Lewis structures, right? Lewis published a paper in 1916 that is now a citation for chemical breakthrough from the ACS, which is even better than the best prize in the world. If you get one of these, you're you've done something significant and lasting in chemistry. So in this paper, all of you should read this paper if you haven't. He outlines his ideas about how linking atoms together and how they make molecules and what governs that interaction. And he didn't call it the covalent bond, but definitely those ideas became precursor to what we know today as the covalent bond. But he really was the originator of putting atoms together in terms of conceptualizing the bonding between these to make molecules. And today I will show you how we can not just link atoms to make molecules, but also to link molecules to make covalent organic frameworks. So this is, if I was a general chemistry student, I would be able to draw not just the Lewis structure of the atoms and the molecules, but also the framework. Okay, the molecule to the atom is what the framework is to the molecule. Let me explain what I mean by that. A molecule takes the atom, puts it in a very specific geometry, connectivity, and spatial arrangement. Okay, and that's what makes the molecule great. The framework takes the molecule and puts it in a specific geometry, specific connectivity, and specific spatial arrangement. But also you have space within which you can incorporate molecules and control their chemistry. So there's an added advantage to going to the framework. So no student wanted to make coughs. I had this idea since we made Moth 5 in 1999. And I would give this project to every student that comes along, and I give them a vision. We are going to make new carbon-based materials, but the first step is to learn how to connect organic molecules together, and they all run away. And the ones that dare to investigate, they get an XRD that looks like this. Okay, and so when a student runs a reaction and it's supposed to have a crystalline material and they get that, they run away. Okay, and they don't listen to you. And so an undergraduate, it's very easy to sacrifice the undergraduates because they need the experience and they need a recommendation letter. And they need all of that to be done fast. Okay, because they're applying for school. So Annabelle was the person that finally listened to me, and she chose this reaction. This is a well-known reaction of trimerization of boronic ester to make this lovely boroxine ring. And it turns out, if you look at the crystal structure of this molecule, there is a CH interaction with an H interaction with this oxygen to make it planar. So it doesn't take a genius to say, hey, if I connect these together, I should be able to make this structure. And you can calculate the X-ray powder diffraction for this structure so that in case you succeed and you make crystalline material, you can compare that X-ray powder diffraction with the simulated one. And so she ran many, many reactions, and after many, many frustrations and everything, she came to me very excited. She showed that hump to me, but also she showed a very nice little sharp peak at the despacing that we were expecting. Okay, so that was very exciting. I said, okay, this is a good first step. You need to turn the whole X-ray powder diffraction into something that looks like an NMR spectrum. Okay, very nice, sharp, narrow peaks. So she went away and she came back with a mystery. The mystery was we are running these reactions in sealed tubes. She said, Professor, the length of the tube makes a difference to whether the material is crystalline or not. And then immediately we realized that you have water that is condensing out as a result of this reaction. And that water, some of it ends up in the headspace. And that is controlling the reversibility of this reaction and therefore the crystallinity of the material. Once we figured that out, we made a crystalline material. Okay, look at it. Okay, so these are the conditions. This is the special sauce, basically, that with very slight modification, you can make almost any cough now. Okay, I'll show you in a second. But if I was a card-carrying organic chemist, we would have a name attached to that. Okay, but I'm not. We don't have named reaction, but this could be a named reaction. So this is the calculated X-ray powder diffraction, and this is the found X-ray powder diffraction. We do a lot of other spectroscopies to make sure that how complete the reaction is, what bonds, the bonds that we expect to form are forming. The structure is an eclipsed, it's a powder structure, it's eclipsed, it's a staggered graphitic structure. And once you know the conditions under which one can form, you can make another one. This is now, instead of boroxine, you're making boron ester linkages, larger pores. Reticular chemistry comes to work. And in this case, it's eclipsed. You can make three-dimensional structure by having a three-dimensional building unit. And in this case, you have a tetrahedron and a triangle. We know what structures to form. It's either this one or this one. Simulate their X-ray powder diffraction, compare it to the found X-ray powder diffraction. And so in just these slides, I have shown you 2D and 3D. Okay? So this is COF 108, and it's made entirely from light elements and covalent bonds. But look at the conditions have not changed much from Annabelle's conditions. Okay, just the time and slight change in the temperature. I guess more than slight. The original COF, the 2D were at 120, this one at 85. So, so to finish Annabelle's story, when she made the crystalline material, she came back to me and said that she was in love. And I thought, well, she's in love with COFs. I can keep her as a graduate student. And it turns out she met someone. He's a very nice guy, very much worthy of her, okay? And she wanted to stop there and get a job in industry. She's doing very well. Okay. So this is the least dense material known at room temperature after lithium. Only lithium is less dense than this. Okay, so nowadays, the COF field is rising so rapidly. Okay, that's why the high citations. But a COF has to be crystalline. I mean, we are chemists. We need to know what we're working with. But there are many publications that you will see where there are amorphous materials, and they call them POPs, porous organic polymers. Okay, that's basically a Moth, a COF that didn't crystallize, or that the authors didn't work very hard at making them crystals. I sometimes call them poops. I think here it's okay to call them that, but not in a pop conference. Okay, well, you can do boroxine, you can do boronate esters, and you can be more ambitious and do imines. Here's the imine linkage, and we can crystallize these. I'm going to zip through them now. Now notice the students are adding 3 molar acetic acid to imines. So that's to reverse the reaction, control the crystallinity. That's, they call it a modulator. Okay. Hydrazone, notice the conditions haven't changed except adding a little bit of acetic acid to reverse the reaction. Borazines, triazines, this is not our work. This is beautiful work by Arnold Thomas. I don't call these necessarily, they're nice compounds, but these temperatures are very high for organic chemistry. The essence of making these is that you can functionalize them. These are nevertheless beautiful compounds based on the trimerization of nitriles. Polyimide, phenazine, we got scooped on this one by Dongling Zhang. Okay, but look, you can crystallize these linkages in a COF. Who would have thought that you could do that? Okay, you combine these two to make an extended structure that's crystalline. Ethylene glycol added. Our group recently reported urea linkages. Okay, your X-ray powder diffractions are shown here. And guess what? You can also have ethylene linkages. That's carbon-carbon bonds. Okay, material is fairly crystalline. and very stable. This Moth is stable in 12 molar HCl, KOH, saturated KOH, N-butyllithium, butyllithium, methyl lithium. It's very, very stable structure, very robust. Okay, so probably Stephen is sitting there saying, Omar, all of these are powder structures, and you have been bragging about atoms and molecules. So what about single crystals of coughs? Okay, that's the tallest order of all. Well, I promised you that reticular chemistry does work. And so when you add a modulator like aniline, you can modulate the reaction kinetics for the imines, okay? Because this competes with your linker. Your linker is a diamine, so this aniline competes with the linker, and you can control the chemistry and get single crystals. So these are the first single crystals of any 2D, 3D organic material, okay? These are crystals that are very much within the range that you do in a laboratory X-ray single crystal diffraction equipment. And so, did we get the crystal structures right? Yes, but now we know where all the atoms are, and we know what their conformation is, and we can get extra information about what's happening in the pores. For example, from powder, we could not tell that there are water molecules filling the pore. So you get one more step advancement in understanding the chemistry. Okay, so I want to finish up with weaving, and so I just need 2 more minutes, if that's okay. Weaving is the oldest way of making anything, okay, and it hasn't changed in all those years. It has only become more sophisticated and being done faster, but the technique has remained exactly the same. So this is another project where I learned my lesson not to give an ambitious objective to the student. Because if you tell a student to make a cough like this, how many of you would do it? I mean, you have to be a crazy person, right? So I didn't even show this. I said to the student, could you make a molecule that has a crossing like this? And the student immediately said, of course, it's already been done by Jean-Pierre Sauvage. And of course, I knew that. Excuse me. I knew that Jean-Pierre Sauvage made that. So anyway, the idea here is to be able to interweave on the molecular level threads of organics in an ordered way. There's no way to do that. Okay, and I just want to share with you a movie here, if you bear with me. Okay, let's see if I got it right. This is weaving.
That makes it a little easier. But let us go right back to the beginning. That's better still. Now we know where we are. Here's the warp threads that run the length of the cloth. And here's the weft, threads that run across the cloth. But the point is, how does the weft go over and under the warp? It's the heddles that will show how this is done. We'll bring them back. And we'll see what job they do. Up and down, separating the threads. Now for the shuttle which flies across. It's followed by the reed, which puts the weft in its place. The fabric moves on. Now we'll watch all those parts at work, and notice especially how the moving heddles cause the weft to interlace the warp. Warp, weft, heddles, shuttle, and reed. Each plays its part in the weaving.
What do you notice about this? this movie, this weaving. It's complicated. It's hard. And try to do that on the molecular level. But that's where reticular chemistry works. If you can make this intersection, then you can link it up and actually manage to make a woven fabric on the molecular level without having to actually weave like that announcer was describing. So the students said, of course it's been done by Jean-Pierre Sauvage. Well, this is exactly that turn, that self-embracing molecule that he uses to make his catenane. And you have copper that brings these molecules together. And I told her, perfect. Why don't you just put aldehydes on the edges and copolymerize it with a diamine? That's just imine chemistry. And you should be able to crystallize it. Of course, imines by that point have been crystallized over 100 times. So they are easy to crystallize now. And so she did. And now you can see the thread forming in and out. Okay? But Stephen will say, Omar, this is still a moth. There is a metal in it. And so indeed, the metal keeps it together at these specific intervals, but you can remove it and make the truly woven form. This is a non-crystalline material. This is not amorphous, but it's non-crystalline. We know what the connectivity is. It does not unravel, because when you add the metal back, you take the non-crystalline to the crystalline. You can do that many times. The reason I'm excited about this is that this woven structure is tenfold more elastic than the metallated one. And so what I'm trying to say to you is that I talked a lot about rigidity, stability, but what about dynamics? The reason weaving is still an enduring method of making these important materials because you can bend them without breaking. Well, that's exactly what we want to do here, is that we have managed to also take a property of molecules like dynamics and introduce it into the solid state in this, I would say, in a meaningful way. There are some people who do dynamics by having a flexible linker, but why? Why do you have to move the entire framework in and out, breathing the entire framework, which ultimately breaks down because you ultimately break bonds? So these breathing frameworks don't really ultimately, they break down. This is a much better way to do dynamics because the threads can move with respect to each other without unraveling and without breaking any kind of covalent bonds. Okay, I won't describe this, but this is the X-ray powder diffraction. We also learned how to do TEM along the way to make sure we have the right structures, but this is what an idealized form of the structure looks like, and you can see the blue threads and interlacing with the red threads. Well, any kind of structure you can think of can be woven. As long as you can make the intersection and control the angle between the intersections, you can make any one of these. You can make discrete objects, polyhedra like this, that are woven, or you could make extended structures that are variously woven. 2D, you can make chain link, fence type. You can also do your weaving by having interlocking of rings. Okay, so this is a whole new area of chemistry that combines the precision of molecular chemistry, the design reticular chemistry, and the dynamics. So I'll just show you beautiful pictures of all the things that one ought to be able to do. There are many, so I guarantee you that any structure you can think of, any network can be woven as long as you can control the angle between those intersections. Okay, so what have we done? We've extended metal organic chemistry to 2D and 3D, encompassing space within which you can do a lot. In organic chemistry, we have gone from Lewis's dot structures to these many milestones of covalent bond, like polyethylene, crown ethers, and so on, vitamin B12. All of these are triumph of covalent chemistry, covalent bond, to 2D and 3D MOFs, and now weaving. Okay, I want to acknowledge the funding and acknowledge my wonderful students who put up with me and are patient with me. And I want to also point out that we have a textbook written for undergraduate, beginning graduate, explaining all this chemistry of metal organic frameworks, covalent organic framework, all the way from basic science to characterization to applications. All of them are explained in a way that would be very facile for undergraduates.
This is just a guess, but isn't sequestration also an interesting problem?
I mean carbon dioxide.
Well, there's other things you could sequester, like H2.
Oh, yes, yes, yes. There is a whole segments of the community working on hydrogen storage. We've solved the methane storage problem. So in a tank filled with Moth, you can store 3 times the amount of methane than a tank that does not have the Moth, all conditions being equal. So yes, there is a tremendous amount of work being done on not just storing gases, but separating gases, separating organics from water, catalysis of all kind. There's just a whole world out there based on this. Yeah.
So, this is a naive question perhaps, but the video that you showed of the Moth itself, you had a lot of these different red sites all over the structure of your Moth. The implication is that all these sites are equivalent to some extent. Could one envision something where you make selective sites to be inequivalent so that it might bind to different species that you might want to say simultaneously?
Yes, there are many different ways of heterogenizing the pores. The binding sites that I showed they're not really all equivalent. They vary in composition and they vary in strength. So that's one heterogeneity. But you can also introduce heterogeneity by mixing different linkers together or by introducing different functionalities into the pores. You can, we showed that you can put 10 different functionalities into MOF5. So that introduces complexity, it introduces heterogeneity. That's the future of MOF chemistry. We just got through making the backbone, but what you do onto that backbone, like your own backbone, is absolutely amazing. That's just the beginning of this reticular chemistry, is what you do on those backbones. And heterogeneity, the thing that you're picking on or picking up, is the key to capitalizing on that. So for example, if you have a pore that is functionalized by 10 different functionalities, conceptually it looks like a pore or the open site or the active site of an enzyme. The active site of an enzyme is very heterogeneous when you think about it, in terms of composition, in terms of geometry. When metals are present, they're present in different coordination. How do you produce that? You can do that in a Moth without changing the backbone, just pinning functionalities and metal binding units covalently onto that backbone and fashioning the pores for a specific application.
You mentioned doing TEM on some of your framework compounds. I imagine that's not the easiest thing. Under what conditions does TEM work or not work for these types of framework compounds?
You can do now TEM fairly routinely on coughs because there are techniques where you dose, you vary the dosage and you can observe very quickly. You can collect data very quickly. So before your material but there are people also using cryo-EM and they're very successful. Yeah, but in 10 years ago it was much harder. Yeah.
I was interested in those low desert units. I have 2 questions. One is how long did one of these last? How long have you had the Moth in operation?
Yeah, the Moth has been tested up to now 3,000 cycles. The water is still pure, and the Moth is still the Moth that we put in first in terms of X-ray powder diffraction. So the idea behind those water harvesting devices is that they would last as long as the electronics will. And usually the people that know what they're talking about in terms of that, they say about 5 to 6 years. But the Moth, our idea is really to have the brain of the thing be the Moth that you can just place in a box. It's modularized. So,
And how much does the water cost?
well, the water that we produce, at least at the scale that we think we're going to produce these at, is about 1/10 of the bottled water in price, in cost.
1/10?
Cost 1/10. Yeah. So, yeah.
And I was interested in the.
But we're creating water where there is no water. Okay, keep that in mind. I mean, this iPhone, I was told last night that this costs $1,500 now. But because it's mobile and it does something you want. The phone that you plug in the wall, many of the students probably don't know those. They're less than $30. In fact, now you can get them for $5. Right? Nobody wants them. Yeah.
The CO2 part.
Yeah.
What's the minimum partial pressure of CO2 in the atmosphere that would feed it to your?
We are.
Can begin to absorb,
Yeah.
say, 50% of the.
We still can't harvest CO2 from air, but we can harvest it from power plant flue gas. Yeah, that one we need to functionalize the pores even more selectively to be able to get that low concentration.
You mentioned that these structures are pretty mechanical, robust. So in terms of sequestration, what would be like the optimal pressure that these structures are?
Well, I mean, when you harvest them from power plants, the pressure is just room pressure. Yeah, you're not doing that at high pressure. We have done high pressure experiments to see what is the high pressure, meaning John Parisi high pressure, geologic high pressure. He's not a high pressure person, he's a lovely person. But to find out what is the weakest point of our structure. And we showed that, in fact, it's really the metal oxygen bonds that in the end break down under. But this is very high pressure. This is not a practical, in an automobile, we tested to 100 bar, even 300 bar, there's no change in the structure. But then what this student did, it was a Russian student, he then placed strategically linkers in the structure post-synthetically and showed that in fact it can be stabilized, retrofitted almost, to keep the structure from swinging. Yeah.